Okay, we are live. Okay, so hello everyone, good afternoon. Welcome to Valongo Seminars. My name is Luan Ghezi and I'm professor at Valongo, and I also have the help of Douglas and Ariana in the organization of the seminars. And today we have the great pleasure of having with us Dr. Natalie Hinkel. And she's a planetary astrophysicist at Southwest Research Institute, and she studies the composition of stars near to the sun, which she also used to understand the makeup of planets outside our solar system, or exoplanets, since stars and planets are formed at the same time. She developed and operates the largest database of elements measured inside stars, called the Hypatia Catalog. And George Takei, aka Mr. Sulu from the original Star Trek, once said Dr. Hinkel was a trailblazer. So it's with a great pleasure that Natalie is here with us. And I might add that she's also a very dear friend and collaborator. So for me personally, also is a great pleasure to host your talk. So Natalie, good afternoon and welcome. It's a great pleasure to have you with us today.
Thanks, Luan, and I'm glad that that I have a chance to talk to you and all the great people who I see are starting to attend. So I'll share my screen now. Does that sound good?
Yes. So we can see your screen. Okay, it's full screen, so yep. I'll be out of the stream. So please go ahead whenever you're ready.
Great. Thanks again. So today I will be talking with you about the interconnection between stars and planets using stellar elemental abundances to understand exoplanet habitability. So I'm going to start off just sort of back to the basics to get everybody on the same page, and then move forward to understand and talk a bit more about my research. So the way I like to begin a lot of my talks is literally at the beginning, which is, of course, the Big Bang. So when the Big Bang first happened, there's a lot of sort of gas that was created, but within this gas, there was basically only hydrogen and helium. Those are the only two elements that were created in the Big Bang. And so what happens is that as the universe was expanding, it didn't expand flatly. In fact, there were all these bumps and wiggles. And as a result of that, a lot of this newly created gas all collected in these big pockets, and it became so massive that it eventually collapsed in on itself, and out came the first star. And so within this star, like they're huge, they're like 1,000 times more massive than the sun. Within these stars, you have fusion. So you have the temperature and pressure enough so that you could take two separate atoms and you can smash them together and you get a whole new atom. And so actually within these new stars, you can take the hydrogen and helium and you can start building up other heavier elements, for example, carbon and oxygen. And however, these first stars, they live fast and they die young. And when they die, they explode in all these different crazy asymmetric ways all over the universe. But with this explosion, you don't just have hydrogen and helium, you also have these seeds of these other elements. And so the next set of stars is formed mostly from hydrogen and helium, but then you also have these few other things. And so when fusion starts taking place within the next generation of stars, it doesn't start just from the hydrogen and helium. It can start from the carbon and oxygen. And then you get, for example, silicon or magnesium. And this continues for many generations of stars until ultimately we find that most of the periodic table is created in stars. So this is a really great image that I love. It was put together by a colleague, Jennifer Johnson at Ohio State. And what she's done is she's color-coded the periodic table of elements to show you where these different elements originally came from within stars. So the ones in blue, hydrogen and helium, coming from the Big Bang, which I mentioned. But then you have a lot of these different elements coming from massive exploding stars. You have smaller stars that can collide into one another, and then that ends up creating new elements within those explosions. And then sometimes you have dying low mass stars that sort of shed the top layer of the stars, and that's how we get other elements. So I love this diagram because it really shows you where all of these elements come from. Now, like I said, at the Big Bang, you have all this gas and dust. and comes together. And this is true now for even more recent stars. This is an image from the Magic School Bus, which I thought was just funny because it mirrors exactly the hand gestures that I do when I talk about this process. So you have all this gas and dust comes together, out pops a star, but at the same time that these stars are formed, we also get planets, meaning that planets, including our solar system, but also planets outside of our solar system, which we refer to as exoplanets, they're made not only at the same time, but also from the same material. And this is really, really key. And I will come back to this. At this point, the exoplanet field has really been taking off. So this is a diagram showing how many planets we've discovered since the field first started. So the first detected exoplanet was really discovered in 1992, but it was discovered around kind of a weird star, and people weren't sure if it was a planet. But it wasn't until really 1995 that a planet was discovered around a solar-like star. So this is really when people think of as being like the first detected exoplanet, although not technically true. But you can see in this histogram like how many stars, how many planets we've discovered in the most recent years, especially using the radial velocity method, which is when you when the gravitational influence of the planet actually creates a wobble in the star. Or the transit method, which is when you have a planet go in front of the star and it creates a slight dimming in the star's light, which we can observe. And you can see this actually in the solar system. So to date, there are now 4,364 known exoplanets. So this is a huge, huge number of exoplanets. And because of that, because there's such a huge variety of the exoplanets, that means that we can see all different kinds of planetary architectures, so different sorts of geometries, big planets around big stars, big planets around small stars, lots of planets together, all sorts of different varieties. So I really like this video. It's called an orrery because it shows you in a quantitative way all these different kinds of architecture. So like the sizes of the dots correspond to how big these stars and planets are with respect to one another, how quickly they're moving. So there's just a huge variation. And this is even kind of an old video, but you get the idea because we can understand the geometries and get the physical aspect of the systems. Now, what this means for these different exoplanets is that it might be that the Earth and Earth-like geometries might not be the only way that we could expect to find habitable planets. So habitable meaning it would be conducive to life as we know it. So for example, here are a couple of different options. Like on the left, this is a planet that is tidally locked. So similar to the moon, where we only ever see one side of it, this planet only has one side of itself facing the star, and one side is perpetually facing away from it. Now, it means a really hot, dry day side facing and a really cold night side, but there could be this strip in the middle that has a combination of the hot and the cold, but also perhaps with the inclusion of an atmosphere that you get some circulation going, and that could itself be habitable. The picture in the middle is not actually, not picture, but artist rendition, is not actually of a planet, but it's of a moon. So this is an exomoon, or a moon around a planet outside of our solar system. And so there are ways that perhaps the planet itself wouldn't be habitable, but the heat from the star as well as the planet could make a potential moon habitable, which is pretty exciting. And then finally on the right, you see that the host star is not bright and yellow like the sun, but it's actually fairly dim. And so this is a different kind of star. We call these M-Dwarf stars. And in order for a planet to be sort of comfortable temperatures, the planet have to be much, much closer than we are to the sun. But that doesn't mean that it couldn't be habitable. So there's a lot of different ways that these different astronomical bodies could be habitable to life. And that's actually a lot of what the exoplanet field is about, is trying to understand overall habitability. So the way that we start off doing this really is with the idea that on a planet or on a surface of an exomoon, for example, we want to have liquid surface water. This is really, really key to life as we know it. And, all life needs water. And so we wanted this planet to be at just the right distance that if there was water on the surface, it's not frozen, it's not evaporated, it's in its liquid state. So this is how we first defined the habitable zone. And you might have also heard this be called the Goldilocks zone. So not too hot, not too cold, just right. But the more that we tried to understand ultimate habitability, we realized that this is a jumping off point, but it's not everything. In fact, when it comes to planetary systems, in habitability, it's a lot more complicated than that. So for example, the top left, you can see different stellar effects are important. So we need to know if there's like crazy flares coming off of the star, or what kind of energy it's giving off, what kind of light and radiation. What about the planetary system itself? That's really important. In our solar system, the giant planets in a way sort of act as a barrier for other sort of like random asteroids and things coming in towards the Earth. So it's important to know about the planetary system and the different sibling planets that are going on. And then finally, you have the planet itself. We need to know the dynamics of the planet, what its atmosphere might be like, and what about its surface. That's really, all of these are important. And yet, this doesn't quite capture everything that we need. In fact, when it comes down to it, it sort of looks like this. This is really the story that we're up against, where all of these different properties are very, very important. This is an image from Barnes and Meadows. Here, the green circles are properties that we can directly measure. Orange triangles are used to calculate models, or can be calculated using models or proxies, and the red hexagons are purely theoretical. Now, this is an older version of this diagram. There's a newer version. However, I really like this one because it gets across how complicated everything can be, because it's not because all of these properties are vital to understanding planetary habitability. It's not enough to say that a planet is in the habitable zone, or it's that it's the same size, like mass and radius of the Earth, or even that there's oxygen in its atmosphere. Even all those things together is not enough to say whether a planet is habitable. We have to look at the holistic picture of all these different properties to really get across whether or not a planet could be habitable to life as we know it. Now, there is a lot going on here, and I'm not about to say that I can do all of it. In fact, I can do a small fraction of it. And so what I really try to do is understand how to go from stars to planets and understand the planets around these stars. Now, you might ask, why focus on this particularly? And that's because to date, we do not currently have the technology to measure the surface or even the interior composition of a planet outside of our solar system. It is not possible. We can see the atmospheres of maybe 20 to 40 known exoplanets, but we cannot see through those atmospheres. We cannot see the surface, and we cannot see the interior. And yet, the interiors of these planets and the surface composition is absolutely fundamental to understanding whether a planet could be habitable. So what I do is I bank off of this idea that stars and planets are formed from the same material at the same time, and I use what we can learn from the composition of the star and use that as a proxy to make models of planets in order to better understand the planetary interior structures and mineralogy and what that could mean for habitability. So that's really what I've been focusing on, is going from stars to planets to understand the planets in a better light. Now, I do this by using the Hypatia catalog. So this is a database that I put together probably over 10 years ago and still maintain. It's the largest database of elemental abundances, so these elements inside of stars, for nearby stars. So it currently contains 9,400 stars, all within 500 parsecs. I also include all known exoplanet host stars regardless of distance. I've created this by combining different literature sources of these different elemental abundances, and in total I have 77 different elements. So the plot that you're looking at has all of the different elements that are within the Hypatia catalog and the number of stars for which they've been measured. And I love this plot. It's one of like my ultimate plots, because it really gives you a chance to see what elements we're able to really measure within nearby stars and which elements might be more difficult. I always get the question, so I like to sort of fend it off, is that the Hypatia catalog was named after one of the first known female astronomers. She lived around 400 AD in Alexandria and was very well respected within her community, within her field. She taught a number of different disciplines, but astronomy was one of them. Unfortunately, because she was so well respected, especially as a woman at the time, she was rather brutally killed. But because of all that she did for the field, I wanted to sort of pay homage to her and name my database after her. Now, I told you the Hypatia catalog has a lot of different abundances in it, but also it's available online. So you can access any of the data at hypatiacatalog.com, where you can go and look at all of the different abundances, all the different elements that we've been able to measure inside of stars, filter on different sorts of aspects of these stars as well as their planets, and be able to get to all of these different abundance measurements. One of the things that's pretty rare about the Hypatia catalog is that it's one of the few multidimensional databases within astronomy. Namely, I have elements inside of stars as measured by different groups, and some of those stars have planets. So while in total there's about 350,000 elemental abundances within the Hypatia catalog. So it's a huge, huge, huge database. In fact, we recently updated it to include many more properties, as well as stars and planets. So we focused on creating an abstracted pipeline to facilitate the database's logarithmic growth. I'm the only one who updates the database because I have to go through a number of different filtering processes to add in new data. And so, but more and more people are coming out with new abundance data. So we wanted a better pipeline to ingest the data, as well as new data types that have been coming out from Future Science. For example, new Gaia data or information from the TIC. And because of the back-end development, we've been able to rapidly increase. The previous iteration had about 6,000 stars. Now we have 9,400. And that's because we were able to remove some of the dependencies of the ultimate back-end cross-matching, which has allowed us to expand in a variety of different dimensions. So that's why the database is so awesome and so great as you see it now, because we did a lot of work on the back end. All right, getting back to the science, what I'm going to talk to you about today, I'm going to touch on a number of projects that I've been working on. So first is how the host star is influenced by the presence of a giant planet. So I'll talk to you about how we're able to sort of trace that with a machine learning algorithm. Then about how stellar abundances can be used to determine planetary interior structures. I'll walk you through an actual example of that for a relatively popular exoplanet system. And then I will talk to you about sort of general astrobiological needs and how we can go from the star to the planet to life in order to see sort of biosignatures in the planet's atmosphere and be confirmed that those are actual life signatures and not some other sort of process. So all of this is a way to connect from the star to the planet to the surface as a way to better understand exoplanet habitability. All right, so begin at the top, which is what I always like to do. So let's first start from stars to planets. At this point, 30 years into the exoplanet field, it's basically a fact that if a star hosts a giant planet, so a giant meaning on par with Jupiter, that star is more likely than not going to be enriched in iron. The basic idea behind this is that these giant planets are made predominantly, they have like very huge iron cores to them, and so you need a lot of that basic material in order to form those planets in the first place. As a counterpoint, we do not see giant planets around very small stars because we don't have that basic material. So if we do find a giant planet around a star, that star is likely going to be enriched in iron just because you need this base material. However, the question became, is this true for other elements? Are we able to see enrichment in other like similarly heavy elements, for example, nickel? Or what about other elements that are needed for creating these giant planets? Are they also enriched within these stars? The problem was that despite many, many teams who did excellent work looking at these different patterns within stars with and without planets with respect to different elements, there's been no consensus about any other kind of enrichment stars other than iron. And, people even looked at the same stars and still couldn't agree about any kind of enrichment other than iron. Now, this struck me as being a problem because obviously we need, stars need certain elements in order to build these giant planets. But what I realized is that a lot of these different studies, the way that they would look at enrichment of elements within these stars was that they would do sort of a one-to-one comparison. They'd look at one element and they'd say, oh, these stars have giant planets and these stars don't, and let's see what that looks like. And they just do that one at a time. However, when you're going through and you're building planets, it's not one element at a time. You need different elements in combinations with one another. The way that I like to think about this is it's sort of like when you eat well, you're supposed to eat a salad and eat all the good things because the different vitamins and minerals within that salad work together in order to keep you healthy. So you can take a vitamin supplement and that's okay, but it's, I think, fairly well known that just taking one supplement isn't enough. It's better if you have all these things in tandem with one another. And so I realized that might be the same thing when talking about planets and building planets, is that we don't want them just one at a time. We want these different elements together. So I put together a machine learning algorithm that was able to analyze the different ensembles of these elements with respect to one another to see if we could perhaps see a difference when looking at stars with and without giant planets. So in a very real way, although not in the back-end way, this machine learning algorithm is a lot like Netflix. So I watch a lot of movies on Netflix, and eventually it learns the kind of movies that I like. So say that I like science fiction movies, martial arts movies, and British movies. So it watches these things, and it learns all these different trends that I like. It then takes these trends and applies it to the back catalog of movies that I haven't watched and suggests movies based on that. So it'll suggest, for example, that I should watch Into the Badlands because it's basically all three of those things. And then it repeats that many, many times and learns as it's going along. So very similarly, what this machine learning algorithm does is that it trains on the stars that have known planets, and it learns the trends within those known exoplanet host stars. So we're looking only at the abundances of these host stars, so the different elements within those stars that host giant planets. It learns those trends within those different elements, and it applies that to the predictive to the stars that we're predicting on without known giant planets. And then it makes a prediction score based on the elements within those stars not known to host a planet, and ultimately we are able to get a confidence level on how well on whether or not these stars are likely to host planets based only on their elemental abundances. Now this code is called XGBoost, which is free. It's on Python, and it's an excellent way to determine stars that are likely to host yet undetected giant planets. Now, I looked at a variety of different elements. I looked at volatiles. So these are elements that have a fairly low condensation temperature, that they burn up fairly quickly. They are volatile. So the closer they are to the sun, then the more they're likely to burn up. Then there's lithophiles. So these are oxygen-loving elements, so they tend to bond with oxygen in planets. And then there's siderophiles, which are iron-loving elements. And so I look at these in different combinations with respect to one another, also with respect to iron, because we know already that iron is an element that should be preferentially enriched in these stars. So I was curious of whether the inclusion or exclusion of iron would have any difference in these different ensembles. So first we went through and double checked that everything made sense. When we put in noise, we got out noise. The iron is consistently an important element, so we knew that to be true. And also because it's not currently possible, like I said, to detect to know for sure that a star does not have a planet. We are not able to detect all planets of all sizes at all distances. It's just not in our capability yet. I implemented a golden set of planets where we knew that they were giant hosted planet stars, and we inserted them and sort of hid them into the prediction set and wanted to see what those what the scores would end up giving us. So this is like taking a movie that I know that I love and telling not letting Netflix know that I love it, and asking it to give me the prediction score to see just how well it thinks it knows me. So on average, we found that all those stars with known exoplanets got a greater than 75% probability of hosting a giant planet, which means this is a good test for the algorithm, and that it works actually pretty well, because it means that a lot of our known planet hosts had a high prediction score. So ultimately, what this algorithm was able to give us was a list of 350 stars that had a greater than 90% probability of hosting a giant planet. Now, this is extremely useful coming up for a lot of missions, both NASA and European Space Agency missions, that are going to be looking at a variety of different stars in order to find exoplanets. And so if we're able to take advantage of the different element abundances that we know in these stars, then we are able to go specifically after some of these targets to see if they actually have giant planets. The other thing that we found that was really interesting within this algorithm was which elements were the most important for determining whether or not these stars are likely to host planets. So this is another way of saying of trying to split up a chaotic group into different subsets of the groups. So it's a way of saying, all of these movies have the genre of science fiction, and all of these have the genre of martial arts. So it's taking a very chaotic data set and splitting them into different groups. And so it turned out that the elements that were most important then for determining whether or not stars are likely to have a high prediction score of a giant planet host were iron, which was good because we wanted that to be true, but also carbon, oxygen, and to a lesser extent, sodium. Sodium was fairly high, but it was at the very top when carbon, oxygen, and iron were not there. So we found that these four elements tended to be the most important when trying to determine whether or not these stars are likely to host a planet. Now, that's not to say that all of these elements are specifically enriched in these stars. It means that the combination of these elements were important. So another way to look at this is these plots where you're looking at the different element ratios with respect to one another. These are sort of standard stellar abundance plots. Now, I'm going to sort of ignore what these plots mean, but really what I want you to do is take a look at the different populations that are in red. These are all of the stars that have a greater than 90% probability, and all those stars that are in black, which have a less than 90% probability. And the main thing that you can see is that that these elements, especially for carbon, oxygen, and sodium, which are on the top line, that they're not preferentially enriched. We're not seeing all these red blobs to be greater than 0 along the y-axis. So that's important because it means they're not enriched, but also that the red blobs do not specifically mirror the black blobs, and that we're not just taking a small fraction out and saying that these are exoplanet host stars. So again, this sort of follows up with that, with the fact that we are looking at a combination of different kinds of elements with respect to one another. So not just preferentially enriched. And so, but actually, I don't have to tell you all about this because this is this is the beginning project. But now I'm working with Luan and his student Augusto on extending this to other sorts of planets, other kinds of planet hosts. So stars, for example, that host smaller planets and not just focusing on the giant planets. And so you can also talk to them about this since they've been really diving into this code. Now, taking a step further, now we've gone from stars to planets. Well, let's look at the planet itself. So like I said, it's not currently possible to measure the surface or the interior composition of a planet. And yet it's absolutely important for life on that planet. We absolutely depend on being able to, walk on iron silicates, and that there's different kind of cycles within the planet that allow us to breathe oxygen and, those sorts of things. And so it's important then to understand the interiors of these different planets that we're trying to better understand and ultimately characterize. And so what my collaborators and I are able to do is take the known abundances of the stars, so these different elements within them and we're looking specifically at those elements that are important for planets. So this is going to be iron, magnesium, and silicon, and then also to sort of a lesser extent calcium and aluminum. And then we put them in a state-of-the-art code that is able to determine the mineral physics of the planet. So this is the Exoplex mass radius package, which is available on GitHub through my collaborator, Cayman Unterborn. Now, we did this specifically for a fairly interesting system. So this is the TRAPPIST-1 system. So it's located about 12 parsecs away, and it has 7 detected planets. Now, the TRAPPIST-1 star is actually a fairly tiny, small, cool star. So actually, the system itself is rather compact. So the TRAPPIST-1 system is what you're seeing in the middle in blue. In comparison to the solar system at the bottom, you can see that it's well inside, it fits well inside the orbit of Mercury. In fact, a better comparator to this system, how small the system is to look at the moons of Jupiter, which is given at the top. So this is a very, very small system. And I will note that these are not real photos. But the interesting thing about this system is that there are 3 planets that are within the habitable zone. So we would expect to find liquid surface water. And so it got a lot of people really, really excited because they're like, oh, there's a lot of potentially habitable planets because we have liquid surface water. But when my colleagues and I looked at this, we were like, oh, it seems kind of like a puffy planet. It's a little weird when you look at the mass and the radius of these planets. So what we did is we took the abundances of the host star and we made models of these planets. And so that's what you're seeing now. On the left is TRAPPIST-1c, and on the right is TRAPPIST-1f. So these are known as a phase diagram, where you can see the total amount of that at the different radii, which is on the y-axis. But this phase percent is like a squashed out pie chart. So we can see at the bottom, 100% of the core is liquid iron core. So that makes sense. And then as you move up, you see different perovskites. But the most important thing is that you see a lot of different ices. So you see a lot of water. In fact, TRAPPIST-1c has 8 weight percent water, and TRAPPIST-1f has 50 weight percent water. In comparison, the Earth has 0.02 weight percent water. There is a huge amount of water in these planets. In fact, it's so much that it's markedly different from the Earth, which just basically has this thin sort of veneer of water at the top of it. And this is really important then for coming back to that discussion of habitability. Namely, planets need to have different kinds of geochemical cycles. We need to be able to move different kinds of elements and minerals around the planet in order to keep the planet alive. This is really fundamental. So we have the carbon silicate cycles and different, like the CO2 cycle. We have all these different cycles within the planet that are fundamental. We rely on them. But if you have these huge water worlds, which have just a massive amount of water sitting on top of them, it's very difficult to have any real kind of cycles going on within the planet. On top of that, say that there was life, perhaps it's at that boundary between the ice and the perovskites, that's going to be fairly difficult to even detect any kind of life signatures because it has to get through all of that water signature. It's basically drowned out by the water. And so that's another reason why this is absolutely critical to try to understand the interior structure and mineralogy of these planets, because it ultimately does dictate a good portion of whether or not these planets are likely to be habitable. So our conclusion for the TRAPPIST-1 system is that they are predominantly water worlds, and more likely than not will not have life, or at least habitable conditions on those planets. Now, taking a step further, so the TRAPPIST-1 system, like I said, was a system around a very small, cool star. So this is called an M-Dwarf. And these stars are kind of exciting specifically because they are fairly small. Now, they're small and they're cool and they're dim. They have their main source of energy for transport is convection, which means that they're actually fairly difficult to observe. They have much lower temperatures, and they're much smaller than our sun. They're about 0.6 the mass of our sun, but they live for a very, very long time, essentially the majority time of the universe. But the best part about these, especially with respect to exoplanet host stars, is that we can detect smaller planets around more easily around these smaller stars. So I mentioned fairly early on that the 2 main ways that we detect planets is the radial velocity technique and also the transit method. both of these methods rely on comparing the star to the planet and looking to see how the planet influences the star. What that ultimately means, though, is that we are more likely to find giant planets around stars that are similar to the sun because they create a larger impact. So if we start, not impact on the star, but a larger variation in our ultimate measurements. But if we want to find smaller planets, like rocky planets like the Earth, we need to start looking at smaller stars, because then those different sort of comparisons make it easier to find these smaller stars. So I've actually started working on observing M-dwarf stars to understand them better, especially with respect to sun-like stars. The variation that we see between these different kinds of measurements is kind of hilarious. All right, so going over these smallest stars, I sort of showed this a bit earlier, but so you can see in comparison, we have this low mass star, we have the sun, then we have the low mass star, and then Jupiter and Earth. And so you can actually see that the M-dwarf is much smaller than what we expect for the sun. Now I mentioned that the inside of the M-dwarf star is heated by convection, and a good example of this is when you boil noodles. And so you see that these tend to go around in circles, and which means that a lot of the different light does not escape from it. In fact, if anything, what tends to escape is a lot of heat, and so we end up being able to observe them preferentially in the infrared as opposed to the optical. Now, solar-like stars, or even more massive stars, make up about 22% of stars in the galaxy. You can sort of see this in this infogram. And they're known to host habitable planets like the Earth. And then as a result, they make up 88% of confirmed exoplanet host stars. However, M-dwarf stars, these smaller stars, make up 76% of stars in the galaxy, and yet they make up only about 4% of confirmed exoplanet host stars. So we have a lot of room to grow here. And as I said earlier, it's easy to detect giant planets around giant stars, but it is difficult to detect these rocky planets. So as a result, upcoming missions such as TESS, Cheops, JWST, Plato, etc., are actually going to be focusing more on M-dwarf stars as a way to try to detect these smaller planets, which we're really interested in. So we know that the data are coming. Now, one of the issues is that these sun-like stars are bright and fairly quiet in the optical. In fact, a lot of the telescopes in astronomy are centered on the optical band because a lot of these stars, it's easy to measure them. However, when we get to M-dwarf stars, we can see these bottom two lines in this plot is that their spectra is not quiet. It's actually quite noisy, and it's very, very difficult to measure any of the elements within these lines. However, if you go to the infrared, you can see that the spectra is much cleaner. It's much easier to observe individual elements, and you're actually able to determine the abundances of these M-dwarfs. But like I said, not a lot of instrumentation in astronomy is centered on the infrared. Because part of the problem with the infrared is that a lot of Earth's atmosphere, the water within the atmosphere, actually blocks the light from the infrared, and so we're only able to see really narrow gaps within in the infrared band. As a result, only 150 M-dwarf stars have abundance measurements for them. And when I say abundances in this case, I mean elements other than iron. There are many M-dwarfs that have only iron measurements, but as I said, in order to really understand the planets, we need to know other elements. We need to know not just iron, but also silicon and magnesium. And so to date, only 150 M-dwarf stars have non-iron abundance measurements. And this is in comparison to the 9,400 stars within the Hypatia catalog and the hundreds of thousand stars in larger, further away data sets such as Apogee. And this is a big problem. It means that we are currently unable to characterize these stars and their planets. It's just not a thing that we're able to do right now. Fortunately, though, I realized that this is something that was worth time to look into. And so I was recently awarded a NASA grant in order to try to understand the abundances in some of these M-dwarf stars. So we're using ground-based data. This is from the IGRINS telescope at from UT Austin to observe a number of confirmed rocky planet host stars, these M-Dwarf stars. We'll go through and measure magnesium, silicon, and iron within these stars and create a novel stellar abundance pipeline that's never been created for M-Dwarf stars. So this is taking into account the cooler atmospheres, the different sort of stellar physics that occurs within the M-Dwarfs, and we'll create a pipeline where we're able to easily extract and fairly reliably extract the different abundances within these stars. Then we'll use these elements to better classify planets. Now, this is really what we're seeing on the right-hand side are 4 different planets where we created different kinds of models in order to better classify them. And so this is these are results from Schultz et al. 2020, where we calculated the probabilities of these different core mass fractions of these planets based on whether we knew just the mass and radius of these stars and whether we knew the mass, radius, as well as the composition. And so this approach incorporates uncertainties of the mass, radius, and the host star abundances. And that's why we see some of these probabilities overlapping. So for the star on the top left, so HD 219134b, it has a probability of 100%, meaning that the planet's composition predicted from its mass and radius is statistically indistinguishable from the composition predicted using the host stellar abundances. So it means that the star and the planet match the compositions with respect to one another. Kepler 107c, which is in the top right, has the lowest probability, which is 1%. And so we can say conclusively that this planet does not reflect its host star composition. It appears much denser than we would expect it to be and can be is more likely to be classified as a supermercury, where some planetary process has removed magnesium from the planet in order to make it so dense and not as Earth-like as we might have originally expected. Then 55 Cancri E, which is on the left, it also has a fairly low prediction score, so it's about 7%, which means it can be classified as a low-density super puff planet because you see that the probabilities the distributions are flipped from one another compared to Kepler 107c. So Kepler 107c is denser than we expected, but the 55 Cancri E is puffier than we expected. And then finally, we have K2229b, which is a very complicated planet. We have this 40% probability. Mostly this indicates that we need more data in order to properly classify this planet and whether or not it's Earth-like or it could be some other kind of planet. So for now, it could be tentatively defined as being a supermercury. But all this gets back to the point that we absolutely need to understand the composition of the star and also the planet in order to really understand the fundamentals to these planets and what it could entail. And so this is a good example, of course, is like the Earth and all the different sorts of elements and compositions that we see within the Earth and how we need to then translate this knowledge of our planet, what we know about our planet, to other sorts of exoplanets. Because as I said earlier, ultimately, planets need to be alive. We have to have these different active geochemical cycles that can create space for life to not only happen, but to also to grow and to flourish. And ultimately, we need to know all these different aspects of the planet because they're all linked with respect to one another. We have the atmosphere, the climate, which feeds into the tectonics of the planet, and also the magnetic field. So all these different things are related to one another. So this gets me to my final point, which is not just going from the star to the planet, but also from the planet to the surface. And so talking about life, because ultimately composition is critical for life. If we don't have elements that are present at the correct molar ratios with respect to one another, then reactions can't happen. So this is sort of like baking a cake. If you have, a lot of the ingredients for the cake, but the cake recipe calls for 4 eggs and you only have 3, then you're going to either have a very gross cake or no cake at all. And so we have to have these different important elements that are present in the right molar ratios in order for us to create life. So this is one example of this is photosynthesis, which has a fairly fixed stoichiometry or ratio of these different elements with respect to one another that are required for a reaction. So I understand it's a little weird to show a chemical equation in an astronomy talk, but basically just look at all the different highlighted colors. So what I'm showing is that we need 106 carbon to 60 nitrogen to 1 phosphorus. These are really the key ingredients. We take that, and that is really what's standard across most life on the Earth. This is what we see in it's fairly fixed across like all sorts of photosynthesis and different kinds of plankton. 106 carbon to 60 nitrogen to 1 phosphorus, and what you get out of that is life. So that's actually the first term that we're seeing, and this is biomatters. This is actually life. And then we see this secondary O2 signature, which I will come back. The problem with this is that phosphate is really difficult to achieve. You can source it only via rock weathering, which takes quite a long time. And so so that we found was a fairly interesting thing, because we wanted to see then what this might look like, what the sort of different ratios might look like when looking not just at life, but also about planets and stars. And so we took this ratio, this is also known as the Redfield ratio, and wanted to compare them, like I said, between different sorts of systems. And so we did this looking at plankton. Okay, so showed that, so 106, 16 to 1. Also Earth's crust and bulk silicate Earth. Then we also compared it to bulk silicate Mars to see how those were different. Then finally we looked at the sun and then nearby stars. So you can see that there's quite a large variation between these different different bodies that we're looking at. Now, I can show you this, but also I think more it's easier to look at a plot where you're able to actually see all of these with respect to one another, focusing on phosphorus, carbon, and nitrogen. So the plot in the background is showing all these different bodies on one plot, which means it's very stretched out. You can actually see very quickly that everything from the Earth and Mars is actually in quite a different range compared to stars. And then the zoomed in plot are all of the stars within the Hypatia catalog that have phosphorus, carbon, and nitrogen. And so the one of the main takeaways from this is that we actually don't have a lot of data. There are 9,400 stars within the Hypatia catalog. Only 100 of those stars, only 100 have phosphorus measurements. And of those, only 54, which is what you're looking at here, have phosphorus, carbon, and nitrogen. So that means that this is really difficult to understand these different trends within stars and planets as well as life. Because we don't have very much data. But one of the other interesting things is that you can see that while the planets don't necessarily line up with respect to one another, that actually the stars are more similar to life than we would expect. So you can sort of see that on the background zoomed out plot, where you can see that this little green plankton symbol is actually sort of lined up with some of the stars. So that means that the ratio between carbon, nitrogen, and phosphorus is sort of more similar in stars to life than it is stars to planets to life, which we found to be fairly interesting. Now, going back to why we really want to try to understand this is that ultimately we need to understand the different signals that we're getting from the planet and the different signals that we're getting from life. So I showed you in that photosynthesis equation that oxygen is one of the byproducts that we get from life, and that's ultimately what we're searching for as a biosignature. That's what we're trying to find in different planetary atmospheres. However, there are other geochemical cycles that could create oxygen, so it's super important when trying to see if there's life on other planets that we understand what's going on within the planetary processes, so that way we can see what's created geochemically versus what's created biologically, and do a comparison of those and make sure that the signature from potential life is much, much stronger than what we would expect from different geochemical cycles. Now, I'm almost finished, but I just wanted a little plug because phosphorus is not the only important measure or element that's important for life. Here I've taken that Hypatia plot that I showed you earlier, and I've color coded it to show you elements that are important for rock forming, that are important for life, and both of them. And ultimately what we found is that nitrogen, fluorine, phosphorus, chlorine, and potassium are all very important for life and for forming planets, but we don't know them very well at all when it comes to looking at the stellar abundances. So this is something that I've been trying to talk to the community about, to try to understand these elements with more rigor, so that way we can have a more holistic picture of what these planets might look like. So ultimately, the feature relies on expanding the definition of the habitable zone and really trying to include all these different properties that are absolutely critical for understanding planets as we know it, to invest in machine learning algorithms because they can teach us quite a lot. Machine learning algorithms, it's an easy sort of term to throw around and to try to dive into, but once you really get into the details of these different processes, they can teach us a lot, and they can show us a lot of information that we might not have been able to look at in more traditional ways. And then finally, that interdisciplinary collaborations are really the way that we're going to be going, especially with respect to exoplanets. It's a combination of many, many different fields. Therefore, working with one another, I think it by far is where the field will be headed. So with that, I will take questions. And if you're interested in Hypatia catalog, here's the website. You can also find me online, my website, or Twitter. So thank you.
Thanks, Natalie, for this great talk and this great overview about how stellar chemical abundances are important to understand not only the formation, but also the surface conditions and habitability of planets. So thank you very much. This was a great overview. And we already had some questions here on the chat. So I remind you guys that you can put your questions here in the chat. Even if they are in Portuguese, we will happily translate them. So don't be shy. And we start with this question from Elio. And he asked you, he's interested in the Hypatia catalog. So how do you combine the different abundance from the literature?
No, this is a great question that I get all the time. So I don't weigh the different abundances because there's too many to do that. Like I said, I have about 215 different catalogs in my database right now. And so what I tend to do is I treat them all fairly evenly. And so the way that I handle this is that I say you have multiple groups have measured the same element in the same star. I take the median value of all of those measurements, and that's what I say is the ultimate determination for that element in that star. But then also, I then use the variation, the range between those different measurements, and that's what I take as being the error. I call this the spread, because that's really the variation that we're seeing across these different groups. And so I think that's the best way to really indicate how well or how we don't measure these elements within these different stars. With that being said, all of this is available on the database, where say that you've determined that there's a certain data set that you would not like to use in your analysis. You can actually remove this from the data that you're looking at on the database, or if you want to download the data, so you can remove it and exclude it from the information that you're looking at. So I've left, while this is my determination, it doesn't have to be yours. So you can go through and if, say you only wanted to use a handful of different data sets, you can also do that too. So there's a lot of data here, and I wanted to make it as accessible to people as possible, mostly so you didn't get overwhelmed.
And I'll take the chance that you mentioned this about the different groups and different determinations. So can you just make a quick comment to the audience on the difference that you find for the abundance of a given star? So are they big? Are they small?
So in general, I think silicon is the most consistently measured element. Most people tend to, like, the errors on it tend to be fairly low, the spread very low. Iron is actually really rough. You'd think that because it's measured by almost everybody, it's like the default thing that everybody measures, that it would line up, but I think it actually works the other way. So it took me some time to be able to say this in public, so I'm going to say it now. But in general, the average spread in iron is 0.36 dex. And
wow.
For those who might know, the standard error on iron is 0.05 dex. So, so this is a huge variation between the different groups, and it's a little painful, but that's that's just to show like how much data there is out there and how much room we have to work with. And I do stress that like I don't think that anybody's wrong in this. I just think that we need to try to work to be more standard. The stellar abundance field has been around for probably about 40 years, and there hasn't really been a consistent way that we've compared our data with respect to one another. Some people will pick a benchmark and compare to that. Other people do some statistics, but it's never the same. So I've noticed now, and I'm grateful for that, there are more people coming out with like benchmark stars of like different stars at different spectral types. And as long as you match those, then everything should be more consistent. And I think that's a pretty good way to move forward.
Okay, thanks. So we have another question from Helio. So he mentions that Da Silva et al. 2015 used ESO-spectra to look for chemical abundance and exoplanet trends. And they point to vanadium as being an element that's more abundant in planet host stars. So have you found something similar?
So this was exactly the point that I was trying to make earlier. For every one paper that you say that will point out one element is enriched in something, I can show you 3 more that haven't found it, even if they looked at the same sample or set up a similar kind of thing. And so no, I didn't find that. In fact, I don't think vanadium was very high at all in our importance features. It was in the middle. Yeah, so that's the problem. Literally, iron is the only one that anybody can agree on. All the other ones are just kind of up in the air, and it's not for lack of trying. We've gotten these groups together to talk about it. They've used the same data. We've had large papers, large collaborations to try to work on this, and so unfortunately, it's just sort of a product of different groups coming together at different times, and so no, I haven't seen vanadium.
Okay, thanks. So continue on the questions about specific elements. So we have a question from Iana. So first, she thanks you for the really nice talk. And you mentioned the high abundance of sodium. So have you discovered other unexpected elements or group of elements in this analysis, something that you are not looking for, didn't expect to see?
So sodium actually was the one we weren't expecting. So carbon and oxygen could kind of make sense. You need the volatiles in those large gaseous planets. Okay, that made sense. But why sodium? So we didn't find like any of the other ones to be weird, but sodium that kept coming up at the top, consistently at the top. So that was the weird one. I was even talking to one of my collaborators, and so Cayman Unterborn, I work with him a lot, and he's like, well, sodium makes sense for rocky planets, but these aren't rocky planets. So it's actually something that we're still not certain on why sodium would be preferential. And so it's something we're still trying to consider. And yet it ended up coming up too often to ignore.
Great, and now an even more tricky element. So Eduardo wants to know about refractory elements whose abundance varies with age. So could lithium fit in this approach of predicting planet host stars?
Right. So yes, lithium could, but at the time I didn't have it in the back end to handle it. So lithium is a very tricky element. In fact, it's so tricky that most people don't even express it in the standard DEX notation. They actually leave it as an absolute value because it varies so wildly. And so at the time that I did this, the backend really wasn't able to handle it because we would convert everything to be in the DEX notation, but then it made some weird numbers for the lithium. And so now we're able to handle it better, but you still have this issue that it can just dramatically change between stars. So say, for example, that you have a star that has dredge up, which can definitely happen. Then there's going to be lithium enriched. Then is that an indicator? So lithium is definitely an element to look at, but it needs very, very special attention, which I don't have a student to look at yet. So it can definitely be added in. And now that the backend is much more robust, we can do that. But yeah, I just haven't had a chance yet, unfortunately. But it is on the list. And on top of the thing you sort of also mentioned is about seeing how these different abundances might vary in age and with the planet prediction and the zeta sub thing, but also determining age is a very tricky thing. So there's a lot to do here.
Yeah. Okay, thanks. So let's move to the next question. So Pedro wants to know if before we knew that iron is an important chemical link between stellar hosts and giant planets, was this expected at all?
I think the answer was tentatively no, but it was discovered fairly early on. So the first indication of this was in 97. So if you remember, it's only 2 years after the first planet around a solar-like star. And even then it was found in like 2 stars. So it was unexpected because it was such a new field and we only had a handful of things. But the more we kept finding it, the more we realized that it actually did kind of make sense. But it did take some time to try to wrap our heads around it. So it's sort of a chicken and the egg thing, because it was sort of found out fairly early on that this might be true. It sort of colored the rest of the thoughts. But the first paper was like, yeah, it was kind of unexpected, but we didn't know what to expect of anything, really.
Yeah, okay, thanks. So while I wait to see if there are some new questions pop up in the chat, I'll make one. So I noticed that when you show the table of the ratios between phosphorus and carbon, the sun is quite different from nearby stars. So what's the deal with that?
Right. The sun is totally different, which we thought was really, really interesting. So we think actually that I didn't show all the plots from that paper because that would just have taken way too long. But one of the things we found is that the sun was consistently different when we looked at, carbon, nitrogen, phosphorus. We also threw in silicon just to see what it would look like. And the sun was consistently different. And so part of this, we think, is that one, we know that the sun is not quite normal to all of its like solar twins. If you look at stars that have similar temperatures and surface gravities and things, the sun isn't quite the same. But also that the thought is that from what we looked at, that the sun is more enriched in phosphorus compared to a lot of other stars. And so one idea behind this, of course, this is on small number statistics, so this should be taken with a grain of salt, is that stars might need to have essentially some extra phosphorus, so that way when the star is formed and then you have the planet, that you have some extra phosphorus left over. Most phosphorus actually goes into the core of the planet. It binds with iron and goes into the core. But if you have extra left over, then that can go onto the surface and then made available to life. So I forgot to mention this, but phosphorus is core to like DNA and RNA, and so it's actually very important for life. And so it might be that the sun is an example, one data point example, that we need extra phosphorus in order for some to actually get to life by the time all of the fractionation and everything happens. And so, yeah, so we thought that was actually really interesting. And also that those ratios of the sun were more similar to the life than anything else in between. We were not expecting that at all.
And that's really cool.
It is, but and it's nice too, because we compared to other planets in the solar system, which we have the the luxury of understanding the compositions of, but that's not going to be the case for any exoplanets. So sort of showing, loosely showing that you can go from the star to maybe the life. Mm-hmm. So that's nice, because we know we can get star data. So that's kind of a benefit. I mean, again, grain of salt sort of thing. We have 50 data points, but also a little optimistic.
Okay, so I see one last question here on YouTube, but I cannot put it on the screen yet because it doesn't appear on StreamYard, so I'll read it to you. So Douglas asks, are M-stars the future for habitable planet search?
I think it's one of the futures. I don't know if it's the future. I think it's nice. I think it's nice to be able to look things at different fronts. And so I started focusing on it because I think we will find, more likely than not, the majority of rocky planets around M-dwarf stars. Now, whether or not they're habitable, there's a lot to that. M-dwarfs are, like I said, they're cool, and they're hard to measure, but also they flare a lot, and we don't we don't actually know a ton about them. I've just sort of been calling them like the forgotten stars, because if you go and look at the literature, there was almost nothing on M-dwarf stars until maybe 5 years ago, when people started realizing that we could detect rocky planets around them. And so we don't know a lot about them, and yet that's it. We need to in order to understand their planets. So right now, I think it's a very good direction to go in. Whether it's the future or one of many futures, I can't say. But obviously, I've invested myself and my time into it, so I think it's a good direction to go in.
Great. Okay, Natalie, thanks. So that brings us to the end of the quest. Oh, no, okay, sorry. There's one more here. So this is the last, now it's the last one. So I'll put it here when it appears on StreamYard. Let's see, okay. Still on the prediction approach, so Eduardo asks, does it take into account effects of galactic chemical evolution? If so, how?
It does not right now, partially because when I started this, when we were using the machine learning algorithm, the stars were only within 150 parsecs, so it's a much smaller chunk of the galaxy, meaning that any sort of galactic chemical evolution be fairly minimal. With that being said, we did remove any potential thick disk stars based on their kinematics, not the elemental abundances. Didn't want to have a circular argument going there. So so we did remove any potential thick disk stars, but all these stars are thin disk, 150 parsecs from the sun. So we don't imagine that there would be any real galactic chemical evolution trends for something this small. Now, if you were to expand it to something like Apogee survey, then no doubt you have to absolutely take that into account. But I think for now, yeah, it wasn't going to be a big indicator. We did, I think, quickly look into it, but it didn't result in any real change.
Okay, thanks. So now that brings us to the end of the questions. So thank you very much, Natalie. So Mariana also thanks you for the great talk. And I again thank you for such a nice overview of how chemical abundance can be used to study planets and habitability. And again, oh, okay, so Eduardo also says here, so thank you very much for the answers and a really nice talk. And with that, I leave you to say any final words that you might want to add for people who are watching.
Yeah, thank you all for listening and for coming. I really enjoyed talking to you all. Thanks for the great questions. It was super useful. The machine learning algorithm is on my GitHub. My username is Hinkel. Like I said, hypatiacatalog.com is where you can get any of the elemental abundances. You can get it on the website itself. You can also download it through our API. I'm on Twitter. Feel free to email me with questions or get a hold of me. I also do a lot of science communications, so I put a lot of this stuff on my website. So if you have any questions, let me know. I'm more than happy to answer them.
Great, Natalie. Thank you very much. We have a final message here from Pedro, also saying it was a great talk. Thank you so much. And for me, as I said before, it was a great pleasure to host your talk, because we not only work together, but I think you're a great astronomer. So thank you very much. I use the Hypatia database, so thanks for that too.
Yeah, and I wish I could like send you all stickers. Normally when I give talks at places, like I bring stuff, so I'm sorry that I can't. Hopefully someday.
One day we'll bring you to visit Rio, and then you'll bring the stickers for us.
Yeah, exactly. Yeah, and thanks a lot, Luan. I really appreciated this. It was, nice to see your face.
It's good to see you too. So thank you very much, Natalie, and thank you very much for all of you that attended our seminar. So this was the last seminar in our current semester, which is a little bit shifted, it's a little bit delayed. So we'll make a short pause and we'll be back in April with lots of more interesting talks. So stay tuned and follow us on our social media to get the announcements of the next talks, okay? So thank you very much, everyone. Have a great afternoon. See you in the next semester of the Valongo seminars. Bye-bye.